Hey everybody, this video lesson is going to cover Lewis dot structures. We're going to spend some time talking about what they are, and then we're going to talk about how to draw them. Lewis dot structures are one of the ways that we represent localized electrons. Localized electrons are meant to be or represented as stationary. Even though we know that electrons aren't stationary and they're always in motion, these models show the electrons staying in place and in fact staying on one particular atom or being shared between two atoms. Now, there are multiple ways to represent the localized electron model, and Lewis dot structures are just one of them. Other models include the VSEPR models and also 3D Lewis dot structures, which we'll talk about in a minute. Now, in the localized electron model, or models, the electrons are assumed to be localized on a particular atom. They're not really in fact localized or staying stationary, but we imagine them as they are that way. Electrons can be described in two ways, as a lone pair of electrons or a bonding pair, which is shared between two atoms. As I talked about in the last slide, there are three ways that we're going to talk about local electron models. The first is the Lewis dot structure, and the other is the VSEPR model. Now, 3D Lewis dot structures are something that you did probably in a previous chemistry classes, but these are the models where elements are drawn in three-dimensional ways with dotted lines, for example, and wedges to show atoms in a three-dimensional way, showing length, width, and depth. But we will not have to worry about doing anything like this for the AP test. And as such, I won't be expecting you to know how to do those, which might be a reason to rejoice for some of you. But we do plan on doing discussing at great length the Lewis dot structures and VSEPR model, or electron geometry. Now let's talk about Lewis dot structures. They show how the valence electrons are arranged among the atoms of a molecule. They reflect a central idea that stability of a compound relates to the noble gas electron configuration. A noble gas electron configuration, remember, has 6 electrons in the p orbital, or in other words, if you consider all the valence electrons in the highest energy level, we're looking at 8 valence electrons, also known as the octet rule. Now, we'll talk about the octet rule as our guiding principle behind drawing Lewis dot structures, but keep in mind this is AP chemistry, so I'll expect you to know a couple of the variations or the exceptions to the octet rule. Now, the duet rule is one that applies to hydrogen only, because hydrogen is full after it bonds with one other element and shares 2 electrons. Hydrogen's full with 2 valence electrons, hence the duet rule. But typically, elements will share or exchange electrons in order to create a stable electron shell, which is represented by the noble gas or the 8 valence electrons in the highest energy level. In other words, atoms will either share or donate electrons until they have a stable valence electron shell, or essentially surrounded by 8 electrons. So here are the rules for drawing Lewis dot structures. This is very similar to how I would teach it in a regular chemistry or honors chemistry course, so pay attention. The first thing that you want to do is determine the total number of valence electrons. In chemistry, I like to call this my electron bank. I'm going to total up all the valence electrons of all the elements of the molecule and put them in my bank, a piggy bank, so to speak. And then as I draw my molecule, I'm going to start to remove electrons from the bank until my bank is empty, like taking cash out of your savings account or checking account. The premise behind a lot of these Lewis dot structures is the orientation of a central atom and the bonds around the central atom. So typically what will happen is you'll draw the central atom first, unless there are 2 central atoms or 3 central atoms. The next thing you'll do is attach the ligands to the central atom using single bonds first. After that, you will attach lone pairs of electrons to the ligands working outside in, and finally put any extra valence electrons on the central atom as lone pairs until all the electrons in your bank have been used up. Once you think you're finished, you check for octets and duets in all the elements, including the outside elements and the inside elements of the Lewis dot structure, and it may be necessary to double or triple bond if the central atom needs more valence electrons to satisfy the octet. This will make more sense to you once I do an example. Now I want to show how to draw Lewis dot structures for these 3 molecules using the same steps that I showed you on the previous slide. First thing I'm going to do is I'm going to add up all the valence electrons of the elements in the compound. So I've got 5 valence electrons for nitrogen and 3 hydrogens, each of which have 1. So if I total up my valence electrons, I have 8 valence electrons. Now this is the total number of valence electrons that can be in this molecule altogether. That includes bonding pairs of electrons and electron dots. So the next thing I'm going to do is I'm going to draw in the central atom. In this case it's nitrogen, because hydrogen can never be in the middle. It's always going to be a ligand. It's worth noting right now that the vocabulary term ligand refers to any element bonded on the outside or not the center of an atom. So I'm going to connect my ligands using single bonds, and when I do that I use up some electrons from my bank. If you can see, I have now 1, 2, 3 single bonds, or representing 6 electrons. So I'm going to subtract 6 from my bank, which leaves me with 2 electrons left over for my dots. Now my dots are going to work outside in, and I check, and hydrogen can't take any dots because it's already singly bonded. Hydrogen is full at 2 electrons, and so each hydrogen is full, 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 and so my remaining 2 dots go onto the central atom in the form of a lone pair. Now I check to make sure everything has 8 valence electrons, or 2 in hydrogen's case. As we already talked about, hydrogen is singly bonded, so it's already good with 2 and 2 and 2, and nitrogen is surrounded by 3 bonds, which represent 6 electrons, and a pair, which is 8. So this is my finished product of NH3. Now the next one is a little bit more difficult. Definitely going to be more difficult than the last one. This is ClO3, so I total up my valence electrons. 7 from chlorine, 3 oxygens, each have 6, and I don't forget about the polyatomic ion. Since it's a -1 charge, I add 1 to my bank. If I total all these up, I get 26 total valence electrons in my bank. Now I'm going to start by putting in my central atom, which is going to be chlorine in this case. And then I'm going to single bond it to all my ligands, which are all oxygens. I'm going to subtract 6 away, leaving me with 20 electrons dots to put in around the outside first. So I can put 6 dots per ligand, because they're already bonded once, so I can put another 6 after it. So that's 12, 14, 16, 18, which leaves me with 2 more dots to place, and those go on the central atom. Now that my central atom has a pair of dots, I double check to make sure everything's got 8 on the outside. Oxygen's got 1 bond and 3 pairs, that's 8, 8, 8, and chlorine's got 3 bonds and 1 pair. That makes 8. Now since this is a polyatomic ion, there's one last thing I need to do, and that is put the molecule in brackets to represent a polyatomic ion with a charge outside the brackets, which basically means that somewhere within these brackets there's 1 extra electron, and that can be accounted for in the structure altogether. And the last one I'm going to show you is CO2. And the first thing I do again is add up my bank. I've got 4 plus 2 times 6, which is going to be 12 plus 4 equals 16. Next I start with a carbon in the middle, and I single bond to my ligands. And I subtract 4 electrons off, leaving me with 12. So that's my 12 dots. There's 6 dots on the first oxygen, 6 dots on the second oxygen, which is leaving me with no dots left over. Then I check to make sure everything has 8 valence electrons. My oxygens are good with 8 each, but my carbon is only surrounded by 4 electrons. And so what I need to do is actually take a pair of electrons from the outside and make a double bond to the central atom with it. And then I can do the same thing on both sides and take another pair of electrons off the other side and make a double bond to the central atom. And what I have now is carbon now surrounded by 8 valence electrons. 2 double bonds makes 8, and by sharing a pair of electrons from oxygen still gives oxygen access to those pairs of electrons, but now carbon is also sharing it. So oxygen didn't actually lose any electrons, it just is now sharing its dots with the center atom. Now some of you might default back to your training from biology class, whatever that was, and you'll take carbon with its 4 valence electrons and oxygen with its 6 valence electrons and try and match up unpaired electrons to make double bonds. Now that's completely legitimate for this particular Lewis dot structure. Notice how those two pictures match each other. But this little electron dot matching method will not work for something like the chlorate polyatomic ion that we made in the middle. It just won't. because you'll draw chlorine with 7 valence electrons, only leaving you with 1 unpaired electron, and that'll only allow you the function of making 1 single bond. But in fact, chlorine can make 3 single bonds. In fact, all elements, as long as they follow the octet rule, can make up to 4 bonds to any particular element or elements that they so desire to make. And so you can no longer be tied down to the idea that only carbon can be in the middle or only oxygen is in the middle. You can now think anything can be in the middle because electrons are not tied to a particular element, but rather shared between other elements that may need the electrons to satisfy their octets. Of course, as we talked about, there's some octet rule breakers. And the first one I want to talk about is boron. Boron tends to be stable with only 6 valence electrons. And so, I don't know, it's the hexagon rule or hextet rule. Okay, boron does not need a full valence, 8 valence shell. So that's the one that you need to know that it's okay less than 8. Now the next one next two you need to know about are central elements with valence electrons beyond the 3rd energy level can utilize the d orbital and have more than 8 valence electrons. And what that means is, or what the implications to that are, is anything in a p orbital, 3rd energy level or lower, that's sulfur, arsenic, phosphorus, and in some cases selenium, can make more than 4 bonds. And in fact, you'll see these pretty commonly with sulfur or phosphorus in the middle. If you're looking closely, you can see sulfur is surrounded by 4 bonds and a pair. And if you're counting total valence electrons there, 2, 4, 6, 8, and a pair is 10. In arsenic's case, it can also be surrounded by 10, in this case 5 bonds. Like I said, you'll see this most often with phosphorus or sulfur. So here's the last slide of this little presentation, and it's drawing Lewis dot structures for these 3 octet rule breakers. Here are 3 octet rule breakers. The first one is boron trifluoride. This one has boron in the middle with only 6 electrons bonded to it, which is completely fine for boron. The next one is PCl5, and you'll see phosphorus in the middle with 5 bonds times 2 or 10 electrons to it. And finally SF6, which is interesting because it's a gas, and when you inhale it, it has the opposite effect of helium. In fact, if you inhale SF6, it lowers your voice a number of octaves, so it sounds like you're talking like Darth Vader. But anyway, I digress. This is the Lewis dot structure for SF6. Well, everybody, that takes care of this video lesson on Lewis dot structures. Thanks for listening.